Howdy everybody. Welcome to another video lecture in trigonometry. In particular, welcome to part 2 of our video lecture series on the law of sines. Now, in this second part of the series, we're going to be wrapping things up by talking about the ambiguous case for the law of sines, what it's about, what we have to do to work with it, and then we're going to work on a bunch of problems that help exercise our skills and new knowledge, and then we're going to conclude the video with a brief talk about area formulas for triangles because there is a convenient area formula that we can introduce. Now, if you have committed a cardinal sin, and in my class and in my video lectures that would be the cardinal sin of not watching my glorious previous video, shame on you, go watch it. I'm going to put a link in the description of this video so you can go back and watch it easily and find it if you have not found it already, but it is important that you come into this video with a decent understanding of the law of sines for the previous two cases we handled. We're going to do a recap, but it's going to be a very brief recap. So make sure you know what you're doing before you delve into the tricky material of the ambiguous case. For my students at the University of South Florida, remember we are still in section 6.2, the section that never ends, the never-ending section. So if you want to make sure that you have this video lecture up alongside, say, your homework, or even just alongside more resources, make sure you're looking at the right stuff. So what did we cover last time? Well, last time, as I'm sure you'll recall, we talked about the law of sines. We specifically said that if we are given any triangle of any sort, we will always find that if we take sine of an angle in the triangle, remember we label them A, B, and C, and divide it by the length of the side opposite, that the fraction we've made will be equal to any of the other fractions of that type that we come up with. So, if I compare sine of A divided by little a to sine of B divided by little b, they are equal to one another, and so are sine of A over little a and sine of C over little c, and so are sine of B over little b and sine of C over little c. All of those pairs of fractions are equal to one another under the law of sines. It doesn't matter whether you are a right triangle, if you are a triangle with an obtuse angle, if all you've got are acute angles, it always works. Now, if you're thinking back to the video, you may think to yourself, hang on, didn't we only work with certain types of data? You're right, we did. Good memory. If you recall, last time when we were going through the material, we found that if we wanted to solve problems or solve triangles with the law of sines, we had to make sure that in our data we had an angle and a side opposite. There was more to that discussion, but at least we need an angle and a side opposite. And to ensure that we have that data, to ensure we have the correct types of data, we can only work with certain formats of information. We can work with data given to us in the angle-angle-side format, meaning two angles and the side adjacent to one of those two angles, precisely one. We can be given angle-side-angle information, meaning two angles and the side adjacent to both of them, which is the side in between the two. We also could be given information in side-side-angle format, which is our ambiguous case. It can be any of those three types of data, but as long as we're given one of those three types of data about a supposed triangle, then we are able to use the law of sines fruitfully to get more information about the triangle and solve the problem or solve the whole triangle. You'll also notice that I've included some more information in the box. Last time, we began by just introducing the law of sines as I've written it in black, and we gave either these pictures or very similar ones. But we also found out, through working with the law of sines, that we could rewrite the equalities that we got in this blue format, taking the reciprocal fractions to the ones we were initially given. Those will work just as well, and actually, in some circumstances, for example, if we want to solve for a specific side length, they may in fact be better, but they give the same information. The other thing is that you'll notice in my pictures I use h to mean vertical height. That is, the height we would get if we inscribe a right triangle as I've done in both of these pictures. It's important to remember that we need to be able to draw a right triangle inside of our given triangle or outside of it at some point, because eventually we're actually going to have to calculate this value h again. More on that when we get to it. All right, that's enough dawdling in the past. Time to move on to newer and more ambiguous things. So we have the ambiguous case. The ambiguous case, as we mentioned before, both in this video and in the previous one, is the case where we are given SSA data about our supposed triangle. That means side, side, angle, and in this case, what we really mean is, in these two sides that we were given, one of them is adjacent to the given angle, and the other one is opposite the given angle. Now, why is this an ambiguous case? Well, it's because actually when we are given SSA data, strange though it may sound, we don't know for sure that the data we were given belongs in truth to a triangle. It is possible to give somebody data that looks as if it should belong to a triangle in SSA format, but it turns out that actually no such triangle exists. You can search all you like, but the data just does not belong to any triangle, even though it looks like it should. That's the ambiguity in the SSA case. We have to check first to see if the data we were given actually belongs to a true triangle. If it doesn't, then our work is done. We can just say no triangle exists, and we can move on to bigger and better things. If a triangle exists, or strangely, if two exist, then we're going to have to do a little bit more work. Now, to evaluate the information that we are given and to see if a triangle is possible, or if two are possible, we need to break this down even a little bit more. And it turns out the right way to break this down is to focus in on the type of angle we're given. So, to begin with, we have the situation where we're given an obtuse angle. If we are given an obtuse angle, then there are two possibilities associated with our data. I'm going to call them cases. I suppose if you want to think of them as subcases, you can. That's a little bit fussy. One important thing I should note, though, is if you look at the drawing I have to the right, I don't call my angles A, B, or C in this picture, and I don't call my sides little a, little b, or little c. Now, why is that? Well, it doesn't matter as much in the obtuse angle case. However, in the acute angle case, you are going to have to use a formula to help you sometimes. If I were to give you the angle names A, B, and C, and the side names little a, little b, and little c, when I write the formula down, either I'm going to give you one specific version of the formula, and then you would have to figure out what all the other versions of the formula look like, which is a bit of a pain, or I'm going to have to write down a bunch of different formulas and take up more space and give you more notes to take. Instead, I'm going to be a little bit more generic. Remember, since we're being given SSA data, we have to make sure we include the A, otherwise we just have an SS, and that's just no good, historically speaking. We have to be given an angle, which I call theta. We have to be given a side adjacent to our angle, which I just call adj, and we have to be given a side opposite, which I call op. That way, when we move through the formula eventually, it will be easy to write it down and we won't have to focus on specific labels for each of our sides. In any case, here are the two possibilities if I am given SSA data and the given angle theta is obtuse. First of all, if I measure the sides opposite and adjacent to the angle, and I find out the adjacent side is shorter than the side opposite, then it is possible to find a triangle that will support the data we were given. In other words, the data we were given does belong to a triangle, and we can move forward with solving using the law of sines. On the other hand, if we measure those two sides and find out that the side opposite is the shorter side, or that it is equal to the side length of the adjacent side, then there is no triangle possible. Now, you may be wondering why so, and I have two types of arguments to help convince you. The first one I like to start with because you can use your hands to do it. Put your two hands together at the palms, leave the heels of your hands, or the heels of your palms, connected, and open up an angle between your fingers. Keep opening it larger and larger, as large as you possibly can. Now you'll notice as you play around with the angle between your hands that you are creating part of a triangle and that the length of the side opposite grows as the angle between your hands grows. It turns out that's also true in triangles in geometry. When I draw angles, the largest angle in my triangle should be opposite the largest side in my triangle. Since we are working with SSA data and we are assuming that our angle, the A, is obtuse, it must be the biggest angle in our triangle. That means the side opposite that angle should be the largest side. So, when we talk about the first possibility, the side adjacent is smaller than the side opposite, that just lines up with what we know about triangles. The side adjacent should be smaller than the side opposite. If that happens, we're just talking about data that conforms to a legitimate triangle. However, look at the second case. We're assuming there's a triangle, so that means the side opposite should be the longest. However, it's not the longest. Well, when we reach a contradiction like that, one of our assumptions must be wrong, and in this case, it's the assumption that we have a triangle. There can't be one. Otherwise, we'd run into a logical contradiction. Therefore, no triangles are possible. There's also another way to visualize this, and I'd like to show that to you right now. What we're going to do now is transfer to one of a number of animations that I've made specifically for this video. In this animation, the black dashed line is the possible third side of a triangle. The two red sides represent the two sides in my SSA data, and the blue arc goes along with the given obtuse angle. You'll notice the side opposite is rotating through a 180-degree arc, seeking to connect with the third side of my triangle and make a real triangle. Now, if you pay attention to this animation, you will actually see that the side rotating through an angle, that is, the side opposite my obtuse angle, is the longer of the two red sides. And so, as we watch, it rotates, it rotates, it rotates, and somewhere around here, it connects with the black dashed line and can form a triangle. And so, therefore, we are able to draw a triangle in this case, just like we predicted we should be able to. However, if we now change the length of the side opposite our obtuse angle, in this case I've made it equal to the adjacent length, you'll notice that no matter how much you rotate that side opposite, we never connect with the black dashed line. We can fold back in on the other red line and create a straight line, but that's not a triangle. In this case, it is not possible to connect three sides and make a triangle with the given information, and so, as we predicted would happen, there is no triangle. Let's go ahead and transfer back to our notes now. We've considered the possibilities when we are given an obtuse angle in our SSA data. The other possibility should be that we are given an acute angle, as I mentioned. So let's go ahead and turn the page and look at what happens when we are given an acute angle. You'll notice that here, the training wheels fall off. Suddenly, it's much more complicated. So let me go ahead and be very careful. In our calculations, because we are going to have to do calculations, we are going to have to calculate the height, just like I talked about previously. Now, in this case, drawing the acute angle theta, the side adjacent and the side opposite, you'll notice that if I drop a line vertically from the top vertex down to the base, I create both the length h and a right triangle, and that from our right triangle trigonometry, we know one way to get h would be to take the length of the side adjacent, which plays the role of hypotenuse in our right triangle we've drawn, and multiply it by sine of the angle theta. It turns out we need h specifically because h is not just giving us the height of the triangle, and it's not just giving us the length of a right triangle embedded inside this triangle we were given, or might have been given. It's also telling us the shortest distance from this top vertex down to where the base should be. This is the shortest possible line we can draw and connect a triangle. Why is that significant? Well, let's look at the first of the cases under the acute angle situation. If it turns out the length of the side opposite our angle theta is smaller than the height h, if it is shorter than the distance at minimum it takes to get from the top vertex down to the base, then we couldn't possibly connect and draw a triangle, and so, therefore, there are no triangles possible. If it should happen that the length of the side opposite our angle is equal to h, then we are able to connect. We are just barely able to connect by simply following this line h all the way down to the base and making one right triangle. Things get a little bit weird in the third case for acute angles. If I calculate h and I find that the length of the side opposite theta is longer than h, so it's longer than the absolute minimum it takes to go from the top vertex to the base, but it's shorter than the length of the side adjacent, there are two triangles possible, which is a little bit bizarre. In just a second, we'll see another animation that kind of helps you make sense of it physically. Finally, if I'm looking at my SSA data and I suddenly notice, hey, look, the length of the side opposite theta is greater than or equal to the length of the side adjacent to theta, I don't need to calculate h at all. In that situation, because the length of the side opposite is greater than or equal to the length of the side adjacent, it turns out that only one triangle is possible. Once again, I like to stimulate your physical intuition for why this is true, so let's go ahead and transfer over to animations once again. Switching over to our animation for the first acute angle case, notice that once again the black dashed line represents the possible base of a triangle if we have one. The two red lines represent the two given side lengths of the SSA data, and we have an acute angle theta down at the origin once again. Acute case 1 is where the length of the side opposite is shorter than the length h. H in this picture goes along with the blue dashed line that you can see. And you'll notice, as the red side representing the length of the side opposite theta rotates through various angles, no matter how we rotate it, it is not able to touch the black dashed line. It's shorter than the minimum distance to get from where an upper vertex should be down to the black dashed line of the base, and so therefore no triangles are possible. Switching to the second case under the acute angle, in this situation the length of the side opposite is equal to the length h, and as we come rotating around, come on, we are suddenly able to connect, but only when my red line and the blue dashed line coincide with one another. Everywhere else, we are not able to touch because we are only the minimum length to contact the base. Only one triangle, a right triangle. Now we're into case 3, the weird case, and look, as we come around, there, we made a triangle, but as we keep coming around, there, we made another one. It's strange but true, and in fact, if you take two pieces of wood, or maybe a couple of pencils, or a ruler and some pencils, or any configuration of straight line objects, you will find if we end up getting SSA data that goes along with case 3 for the acute angle, we are able to swing that side opposite around and make two possible triangles. One of them will create an acute angle at the bottom right-hand corner, and the other one will create an obtuse angle at the bottom right-hand corner. A weird feature of how this particular case works that we're going to have to leverage when we actually work with problems involving this sort of information. And finally, case 4, where the length of the side opposite is the greater of the two lengths. We made a triangle just a few seconds ago, but if you watch the rotation, we don't get to make any other triangles. There's one here, and no matter how else we rotate, that is the only triangle we're able to make. At all other times, we're either not contacting the base, or we're so long that we sink below the level of the base, and we're not able to make a triangle. So, there is only one triangle. Okay, now that you've actually seen what it looks like to have this data in front of you represented physically, or visually, I guess as the case may be, let's go ahead and work on some exercises to drive this information home. We'll return to our notes, and we'll get cracking on some problems. Scrolling down the page, we have our very first exercise. Solve for all possible triangles, if any. We know that the given angle B is 110 degrees, little b is 19, and C is 21. Now, when you are given a problem like this, you may not realize to begin with that this is in fact SSA data. So my recommendation is to always just begin by drawing a triangle. In this case, draw with an obtuse angle, and then start labeling where the information is. That way we know for sure whether it's SSA or not. So I draw a line here. I'm going to just go ahead and act it first as if I have a triangle. So there you go. There's my obtuse triangle, kind of an ugly one, but, you know, beggars can't be choosers. We have B at the bottom left-hand side, which is where I tend to put my angle when I'm drawing triangles. We have little b across from it. And, well, you'll notice that that means that little c has to be adjacent to my angle. It could be over here on the right or over here on the left. I have a tendency to draw on the left. And now we can see for sure that this is SSA data. So let me make a couple of changes to our picture. Okay, so changes I made. Well, first of all, I included the information we were given. I put in my angle, I put in my two side lengths. Second thing you'll notice I've done is I've converted the side opposite B into partially a dashed line, and I've converted the base into dashed lines as well. The reason for this is sort of a visual shorthand. I'm reminding myself that there may or may not be a triangle here visually, so that way I'm recalling that I need to check. That way, both right now when I'm working on the problem and later when I come back to look at my notes, I don't get confused and go, hang on, why did I do that? Now, looking at this, knowing that I'm dealing with SSA information and that moreover, the given angle was obtuse, I know from the rules we talked about just a little while ago that all I need to do is compare the lengths of the sides opposite and adjacent. In this case, what that means is I'm comparing the length of B to the length of C, and I'll notice that B, the side opposite, is less than the length C. If the information I was given went along with a legitimate triangle, this would not be happening. So, there's only one possible answer. This is not a triangle, or rather, the information I was given does not belong to any triangle, and so therefore I can simply stop my looking. It's done. Well, that was kind of anticlimactic. Let's do another one. Okay, same sort of problem. This time we were told that we were given A, little a, and little b. So let me go ahead and draw that triangle. Even though this time my given angle was A instead of B, I'm still drawing pretty much the same picture every time. I already recognize that I'm dealing with SSA data because I see that I was given little a, the side opposite the angle A, and I was given little b, which is a side adjacent. So I've already drawn in the shorthand for the fact that I need to check and find out if a triangle is possible. Now let's go ahead and include our information. And you'll notice that, first of all, I forgot to include my angle. That was naughty. Let's correct that. Second of all, you'll notice that once again, since this is an obtuse angle SSA data case, what we can do is we can compare the length of the side opposite to the length of the side adjacent. And in this particular case, little b, the length of the side adjacent, is less than little a, the length of the side opposite. So in fact, we are able to make a triangle, and now we're going to actually have to use the law of sines. Let me complete the labeling of this triangle, so that way we know what we can solve for. Okay, I added all the missing labels just based on the information I was given to begin with, and now looking at what I've been given, since I have the angle A and the length of the side opposite, I'll want to use that to solve for something. The only other given data was the length of little b. So that's telling me that probably the equation under the law of sines should be the one that involves the angle A and side A, and the angle B and side B. Angle B is missing from our data currently, so that is going to be the thing I'll want to solve for. So I simply note I'm solving for B, big B, and I set up my equation. Sine of big B, the unknown angle, divided by little b, the known side length, is equal to the sine of big A, a known angle, divided by the length of the sine little a known side length. Okay, I want to solve for big B, so the first thing I should be doing is multiplying both sides by little b. That done, I have the equation sine of b is equal to little b sine of a, all divided by little a. Since I want to solve for big B, and since I see that big B based upon two things. For one thing, it's hinted at in my picture, but also for another thing, big A is obtuse, meaning the other two angles have to both be acute angles. I know that big B is a quadrant 1 angle. Since it's a quadrant 1 angle, it is okay for me to use arc sine to get rid of the sine on the left-hand side of my equation. But if I do that, I need to also apply arc sine to the right-hand side. When I say I'm applying arc sine, what that means is I'm taking the number sine of whatever big B is, and then saying arc sine of big B. And since we know that big B belongs to the restricted domain for sine, arc sine of big B reduces down to just big B. On the right-hand side, though, we're going to have arc sine of the fraction little b times sine of big A, everything divided by little a. Now, technically, that is the answer we're looking for. However, we are also going to want some kind of approximation. So my recommendation is put this all into your calculator, make sure you're in degrees mode, and let's go ahead and approximate it out to 2 decimal places. Try to beat me to the calculation. Pause the video if necessary, which isn't cheating. Here we go. According to my calculator, it appears that that makes B approximately 24.45 degrees, with the exact answer being a little bit more cumbersome, but you can still calculate it. Oh, well, check this out. I had one angle, now I have 2 angles, or at least one precise angle and one approximate angle, so now I can solve for the third angle. Using our by now familiar information that the sum of the 3 angles should be 180 degrees, and then simply solving that sum, or that equation sum, adding to 180 degrees for C, it looks like we should get the approximate answer. Whoops, let me get that approximate answer back. Approximately, my calculator was fighting me for a second, approximately 50.55 degrees. Okay, so we have all 3 angles. We have 2 of the 3 sides, so it's just the third side, little c, that we're going to solve for. Now, when you're doing the calculation for little c, you should go ahead and use the precise value for big C, meaning when you write it into your calculator, use the exact phrase arc sine of all this fraction on the inside, then use that to calculate C. It will be messy. If you need tips for how to use that precise value in your calculator, come talk to me or leave a comment. I'll be happy to help you. In any case, we're going to be solving for little b. And since I'm solving for a side length, I think what I'm going to do is I'm going to go ahead and use the reciprocal version of our law of sines. So I'm going to say, okay, I don't know little c. Whoops. I said little c to begin with, and then I wrote little b. I don't know what that was about. But if I want to solve for little c, that means one side of my reciprocal law of sines equation should be little c over sine of big C, and that should be equal to, well, since we were given precise data for big A and little a, what begins with a, we'll go ahead and make the right-hand side all about big A and little a. So little a divided by sine of big A. Okay, the algebra here should be pretty straightforward and obvious to all of you, so try to beat me to it. Multiplying both sides of the equation by sine of big C, we find that little c should be equal to little a sine of big C, all divided by sine of a. And if I feed those exact values into my calculator, I can then get an answer which I'll approximate to 2 decimal places as 55.96 units. If you're finding that your calculation is a little bit different, especially if you're close to the same answer but maybe off by a few tenths or a few hundredths or a few thousandths, what that probably means is you didn't listen to what I said and you used an approximate answer like 24.45 when you calculated C instead of using the exact value. Remember, only round your answers at the very end unless you're directed otherwise. Generally speaking, if you want greatest accuracy, you have to wait until the very end of a calculation before you round, and all of your intermediate calculations should be exact ones. Now that we've done a couple of these problems, you see the basic process. All we need to do is apply the rules that we've already introduced for figuring out whether or not a triangle is possible, and if at least one is possible, how many total are possible. So, for all my students at USF, I'm going to give you a Canvas quiz question. How many triangles are possible if I give you the data, the angle A 62 degrees, little a is 30, and B is 40? With possible answers, A is 1, B is 0, C is 2, and D is 3. So 1, 0, 2, or 3 triangles. Now, I'm going to give you a couple of clues, as is tradition, USF students, so don't you worry. Clue number 1. Look at your angle A that you were given. It's an acute angle, which means you cannot use the rules for obtuse angles. You need to use the ones for acute angles, so make sure you go back and review those. Clue number 2. If you look back through your notes, or through my notes, as the case may be, I'm sure you're going to find very quickly we never had an opportunity for 3 triangles, so I think that you can pretty safely ignore one of these options. Finally, remember that when we are talking about the acute angle case, we're always comparing, or usually comparing, I suppose I should say, the length of the side opposite our angle to the height of the triangle. So make sure that you're considering the height of the triangle and obtaining that before you go further. Now, looking at how long this video has gone on so far, and considering all the possibilities open to me, especially how I can help you do well in this Canvas quiz question and how I can prepare you better, I'm going to go ahead and choose to be benevolent, for I am a kind of benevolent man with lovely, lovely facial hair. Rather than continuing with all the exercises I planned, I am going to stop the lecture after 2 more quick problems. One will be an acute SSA triangle case, where we're going to have 2 possible triangles, and I'm going to show you how to solve for that because that is crucial information. It will also remind you of the basic rules for the acute SSA situation. Then I'm going to do a problem that involves the area formulas that I mentioned at the beginning. For students at USF, I will go ahead and do a live version of a tricky application problem in class. I may have mentioned it at the beginning of the video, I can't recall for sure, but I will do it live in class so you're able to be a part of the problem-solving process in real time. For right now, let's go ahead and move on to the first of our final 2 problems. We're going to solve for all possible triangles, if any. I've already given the game away, but I'm going to be coy in my writing. And the given data is B is 32 degrees, little b is 50, and C is 60. Let's draw that triangle. Now, just like before, we're going to draw our triangle with some sides partially there and some sides indicated, but we're going to be a little bit wishy-washy about them, as if we don't know for sure whether or not we're going to have a triangle. Unlike the previous times, though, remember, and I mentioned this in the hint a few seconds ago, the hint, I need to enunciate properly, even though this is math class, not English or grammar, we need to have the height of this triangle, which I'm going to temporarily represent via this blue dashed line, which makes a right triangle. Remember, this is H. We have to calculate this for the acute triangle SSA case. We didn't have to for the obtuse case. And H is always found as you may recall, by using our information about right triangles. Since I have made a right triangle, the bottom corner has an angle of 32 degrees, and it has a hypotenuse of length 60. What I'm going to do is I'm going to take that length of 60, and I'm going to multiply it by sine of 32 degrees. That way, because I know that sine of 32 degrees should be h divided by 60, multiplying by 60 should get rid of the division, and I should just be left with h. And according to my calculations, I am getting, well, actually I'm getting kind of an ugly number, so I'm going to represent it exactly. And as I've done in a previous video, when I do this exactly, I'm going to write some number of decimal places. So 31.7951, and then I'm just going to put dots to indicate it keeps on going. I want to keep this exact for right now because I want to make sure my comparisons are good. Now that I have h, I need to compare h to the length of the side opposite. And, well, let's see. It looks to me as if the length little b, the length of the side opposite, is greater than the length h. Okay, well, as soon as I do that, I begin thinking to myself, okay, there's two possibilities. Since little b, this length of the side opposite, is longer than the minimum length, the height, then I need to be in either case 3, where there are two possible triangles, or I need to be in case 4. So let's compare the length of the side opposite to the length of the side adjacent. And let's change color back again. We have to do proper colors here. Okay, B is 50, C is 60. Okay, so the length of the side adjacent is greater. Therefore, this is case 3, and there are two possible triangles. I guess I'll keep writing in black for now. Two triangles. Even though there are two possible triangles, it's still not that bad to begin with. We're going to continue to use the law of sines, just like we did before, but I'm going to make some notations that will help us keep track of what's going on. Once again, I've labeled the missing pieces of information, except for the little a piece, but you'll notice now I've numbered them as well. So I have C1, I have A1, and I have little a1. That's all to let me know this is information from the first triangle. So let me go ahead and solve, and it looks to me like since I have big B and little b, and I have little c, the thing I could probably solve for right now is big C1. So that's exactly what I'm going to solve for, and it's going to be the standard setup. Using the law of sines, sine of big C1 over little c is equal to sine of big B over little b. And since we want to solve for big C1, we first multiply both sides by little c in order to isolate sine of C1. And then I apply arc sine to both sides of the equation. When I do that, I have arc sine of C1 on the left-hand side. And since C1 is an acute angle, what I'm going to wind up with is C1 is equal to arc sine of little c sine of b divided by little b. A value I can punch into my calculator, and you can too. And if we round to 2 decimal places, we obtain approximately 39.49 degrees. From here, we can obtain little a1. Big A1. We use a familiar subtraction, and it looks to me like we're going to have approximately 108.51 degrees. I was so eager to find little a, I suppose we should go ahead and do that now. So, I use the law of sines and say little a1 over sine of big A1 equals little b over sine of b. And then we can feed this into a calculator, and it seems that we're going to get approximately 89.47. Okay, This solves the first triangle, and you may be thinking to yourself, okay, but how do I get the second triangle from here? Well, actually, that's not too hard. Let's scroll back up and let me add in the other line we'd expect based upon our animation from earlier. In fact, let me make one more small adjustment because there's something that's not evident in this picture, but it would make things a lot easier if it were more evident. One moment. There you go. More or less the same picture that we had before, but you'll notice I brought it in a little bit, and that's to emphasize something important. The red line that connects big A1 and big C1 is the same length as the green line that connects big A1. Well, actually, let me go ahead and be more precise here. Since it's now our second triangle, it would be big A2 to big C2 down here. Now, why is that significant? Well, you'll notice that what that means is that if I include the little bit of base between C2 and C1, and then the red and the green lines that I've indicated here, I've created an isosceles triangle. The angle here at red C1 and the angle here inside my isosceles triangle at green C2 must be equal to one another. So the angle on the other side, which is the actual angle that I want, from the green line down to the base here between B and C2, will be the supplement of C2. In fact, let me go ahead and write that here very carefully. C2 should be what happens when I take 180 and I subtract C1. For USF students, we'll talk about this more thoroughly in class the next time we meet face-to-face, but for everybody else, this is the information we need to finish off this problem. Since we know that C2 is the supplement to C1, all we have to do is recall the calculation that we did to get C1, and we can subtract that from 180, and that will give us approximately 140.51 degrees. Even better, this makes finding A2 easy as well. See, what we know is that A2, C2, and B added together form another triangle, and that triangle must have 180 degrees in it. So if I want to find what A2 is, all I should have to do is take 180 and subtract the angles C2, which we just calculated, and B, which we began the problem with. We'll approximate this as well to 2 decimal places, and that gives us more or less 7.49 degrees. A very, very small angle, but actually, if we go back up for a moment, we can kind of see that up here at this corner. That definitely looks like 7 point something degrees to me. Finally, now that we know what A2 is, we can solve for little a2, and it will look almost exactly like what we did for little a1. As before, we do some algebra, and then we feed this all to our calculator and get the approximate answer, 12.29 units. And there you have it. Just indicating where that is in my picture up here, although things are getting a little bit tight, we have now solved both possible triangles. One which goes up the line between B and the black dot up here, which is either A1 or A2, down the red line to C1, and then across the base. The other goes from B to A2, and then down the green line and across the base back to B again. Both triangles calculated. It's not hard, but you do have to know the relationship. C2 and C1 are supplements, and that will always be the case with the two angles that we get at the bottom. This angle on the far side will be acute every time. This one here will be the supplement of the acute angle. All right, last topic, and then I set you free. So there's an easy fact we can derive from our standard triangle area formula. If we are given a triangle with side angle side data, that's what SAS data stands for, then we can calculate the area, which is denoted for some reason by K, as 1/2 the second adjacent side to the angle theta times the first adjacent side to the angle theta times sine of theta. Now that may look a little weird at first, however, the picture should help you clear this up. Normally, if we were finding area of a triangle, we would do 1/2 of base times height. Well, the 1/2 is still there. Base is what we mean by adj2. It's the length of the base of my triangle, so that's my base. Height would be played by h, but if you remember from some of our previous calculations, once we've drawn h in, and we have this angle theta at the corner, we can simply take the hypotenuse for the right triangle we've made, which is adj1, and multiply it by sine of the angle theta, and that will give us h. Therefore, 1/2 base times height is the same thing as the formula we've written here, and we can use it in a problem such as the one coming up on your screen. If we have a triangular region that we're trying to landscape, if we have the information about it based on the diagram below, and if we know that it costs $30 per square foot to landscape it, what will the landscaping cost be? Well, hopefully you realize that we need to figure out what the area is for the triangle that we see here, because that will give us square footage, and then we simply multiply that square footage by 30 to get the dollar value. Also, based upon the picture we see here, it looks like we have SAS data, so we're able to use the formula we just got. So, let's go ahead and label things. To keep an apples and oranges, well, let's keep an apples to apples, comparison in our picture here with what we wrote in our formula up above, I've labeled the base as adj2, the second adjacent side is, or the first adjacent side really, is adj1, and the angle between the two sides is theta. So, if we apply our formula exactly as it appears up above, just giving ourselves some space below, we have 1/2 times the base, which is adj2, or in other words, 35 feet, times, adj1, which is going to be 20, times sine of the given angle, which was 30 degrees. And we can simply feed this into a calculator and get 175 square feet. So if you want to know the cost, which I'm just going to write down explicitly here as cost, we simply take $30 per square foot and we multiply it by 175 square feet, which gives us $5,250. And I'm going to go ahead and include that here, even though I haven't in the previous parts of the calculation. $5,250 to take care of this triangular region in landscaping. Whew. All right, guys, that became a little bit of a rush at the end, but I think we've done a pretty good job of covering everything. If you have any questions, make sure to leave a comment or to ask me in class if you're a USF student. And until next time, no matter what you are in relation to me, happy math.